Hello and welcome to this video about data structures. In this video, we'll be looking at the data structure for matrices. There are three attributes for this type: the numbers of rows and columns, and the data or elements of the matrix. The rows and columns are stored as integers or int types, and the elements are stored as real or complex numbers. Here is an example of a matrix written out in standard matrix form. It has 3 rows and 4 columns, so they'll be stored in these variables. The data or elements will be stored in a one-dimensional array, which can be manipulated to behave like a two-dimensional array. We'll start counting from 0 instead of 1 in this matrix type, because this is how computers store information in their arrays. If we want to get the element at row I and column j, we'll use this formula to make the one-dimensional array behave like a matrix of values, so that the element at this location in the matrix will be accessed by this formula in the array stored in the computer program, which will give us this value for this element in the matrix. We could have all of the information about matrix A in one array, with the first and second element occupied by the number of rows and columns, which would be easy to do, but we'd like to store these attributes as integers and elements as real or complex numbers, so it's a good idea to keep them separate for now. Now to look at an example of how this information is stored in a computer. This is JavaScript, and it doesn't support structured types, but they can still be represented by variables that look like structured types, the underlined character acting like a dot or attribute function. There would be a lot of functions associated with the matrix data type. We'll look at the print function first, which is used to display the contents of the matrix. We'll firstly write out the name of the matrix that we'll print out, which is A in this case. Separate print functions will need to be written for each matrix variable. We'll make up a double loop to get every element in the matrix according to its row and column, so that we can write it out as a matrix. So we'll get every location in the array of each element that we're accessing and print them out in a line in order. We'll then write a new line for the end of each row so that it looks like a matrix when printed out. And here's the print bool function to print out the value of a Boolean variable as true or false. Here is the function to set an individual element of a matrix given its row and column. We'll assume that the information is good for this matrix, like that the row input isn't negative or too large. We'll calculate the location of this element that we want to set to have a new value. Then we'll set it to be this value. This function will look at a particular position of the matrix and return the value of the element at this position. We'll calculate the location and get the value of the element at this location, and then return this value to the user. These functions are extremely simple, and we won't use them for more advanced programming, since we'd like our matrices to be processed quickly. More advanced programs may take more than 10 minutes to run, and time needs to be saved when writing these programs. So now to the first of the arithmetic functions, the add function. Matrix addition is extremely simple. The two matrices that are added together must have the same dimensions, and so an error is thrown here if they don't. We'll set the dimensions of the matrix containing the answer called C in this case to be the same as at least one of the two matrices being added together. This double loop spans all of the elements in these matrices. And this line here gets two elements in the same position in two matrices and adds them together, and then places the sum of them in the third matrix or sum matrix. It must be noted that the function for subtracting two matrices is nearly exactly the same except for this line, where a minus sign is written in place of the plus sign. Now to look at the transpose function of a matrix. Here you can see how this function swaps the rows with the columns. We'll now start to create code for this transpose function. The number of rows and columns are swapped for the transpose of a matrix. This is a loop that looks at every element of a matrix. We'll get the location of the element of matrix A, the matrix we're going to find a transpose of. Then we'll get the corresponding location of the element B, the transpose of A. If you look carefully, you'll see that the index variables of B are swapped for this location. We'll insert the value of element ij in A into the location of element ji in B, and so that completes this function. The next function is multiplication, which is a bit more complicated than these other previous functions. Each element of the product matrix is calculated by multiplying elements from the two matrices as shown in this picture. So here's the multiplication function. We'll initialize these variables here. Notice that there are separate location variables for matrices A, B, and C. The number of columns of matrix A needs to be equal to the number of rows of matrix B. We'll set the row and column attributes for matrix C, the product of matrices A and B. Now we'll create a loop that spans all of the variables in matrix C, the product or answer matrix. EL is the sum of products of elements of A and B multiplied together, and is initially set to 0 because it will be incremented in a loop. We'll get the location variable for matrix C so the data can be copied into it. We'll make a loop here to span a row of A and a column of B. These are the locations of elements that we'll look at in these two matrices A and B. We'll add the product of these elements to a counting variable to eventually get the total of all these products. Now we'll insert this value into the matrix C and eventually get all of the elements of C that we want, and thus find the product of A and B. Notice that the order of multiplication is important, because matrix multiplication is non-commutative. The next few functions will test whether a matrix is one of these types. An identity matrix is a square matrix, that is, having its rows and columns equal, that has ones along its diagonal and zeros everywhere else. A scalar matrix is like an identity matrix, but can have any number along its diagonal, as long as it is the same number, with zeros everywhere else. A diagonal matrix has numbers along its diagonal, and these numbers don't have to be equal to each other, although they can be. A zero matrix has all of its elements equal to 0, and doesn't have to be a square matrix. Now to get the function that can tell the user if a matrix is a diagonal matrix. A diagonal matrix must be a square matrix, and if it isn't, we'll return with the value false. We'll set the Boolean variable equal to true or 1, and if we find that there is something that stops this matrix from being a diagonal matrix, then we'll set this value to false or 0. This loop looks at all the elements in the matrix that aren't in the diagonal. These elements must all be equal to 0. We'll get the location of one of these elements and check to see if it is 0 or not. If it's non-zero, then we'll set the Boolean variable equal to false. We can then exit the loop early because we've included this variable in the loop's exit conditions. Then we can return this Boolean variable to another part of the program. This is a function to tell whether a matrix is a scalar matrix, that is, if it is a diagonal matrix with all of its diagonal entries equal. It must be a square matrix. If it isn't, then we'll return false. We'll set the Boolean variable to be equal to 1 or true here. All of the non-diagonal elements must be equal to 0, like in the diagonal matrix, so we'll add a loop to check for this condition here. It will be the same as for the diagonal matrix function. Now we have to check that all of the diagonal elements are equal to each other. We'll load the first element, which is the first diagonal element, into this variable, and check to see if all of the other diagonal elements are equal to it. We'll make up a loop to span all of the diagonal elements. We'll only need one index variable to stand for both the row and column at the same time. If we find that one of the diagonal elements is different, then we can set the Boolean variable to be 0 or false, and we can exit this loop early because this Boolean variable is included as a condition in the loop. And so we can return this Boolean variable to say whether this is a scalar matrix or not. Now to write a function to see whether a matrix is an identity matrix, that is, a diagonal matrix with all of its diagonal entries being equal to 1. It functions as a 1 in matrices. It must be a square matrix. We'll set the Boolean variable to be 1 here for the same reasons that we set it to be 1 in the two previous functions. It must be a diagonal matrix. We'll create a loop to step through all of the diagonal elements. And if we find one diagonal element that isn't equal to 1, then we'll set this Boolean variable to false and exit the loop. We'll now return the variable saying whether this matrix is an identity matrix or not. Now to check if the matrix is a 0 matrix, that is, that all of its elements are equal to 0. Notice that this matrix doesn't need to be square, but you can add this condition if you like, if you wanted it so as to be a member of a ring, for example. We'll set the Boolean variable to be equal to 1 and set it to 0 or false when a non-zero element is found in the matrix. We'll create a loop to look at every element of this matrix. Then we'll get the location of each element. And if we find an element that isn't 0, then we can set the Boolean variable to 0 or false and then jump out of the loop. Then we can return the value of this Boolean variable saying whether or not the matrix is a 0 matrix. So now we have to test these matrix functions that return a Boolean value. We'll have to make functions that construct matrices. We'll start with the 0 matrix. Here is the function definition statement with the variables that it will use. It will be an n by n 0 matrix. We'll create a loop to go to the location of every element in this matrix and set all of these elements to be 0. And then we can make a second function that creates 0 matrices that aren't square, with m being the number of columns passed through a second parameter variable called m. We'll now make a function to construct an n by n identity matrix. Firstly, we'll set every element to be 0. Then we'll set every diagonal element to be 1. It is actually faster to set these diagonal elements twice, rather than to put an if statement inside the zeros loop. And the function to construct a scalar matrix is nearly the same, except that a number m is used as a parameter variable to set every element in the diagonal to be m instead of 1. Now to make a function to construct a diagonal matrix, we'll firstly set every element to be 0. Then we'll set all of the diagonal elements to be equal to values from an array defined earlier in the program. And this is the array containing elements to be put into the diagonal matrix. So I hope that you have found this video to be helpful, educational, and maybe even enjoyable. Please click like and subscribe if you did. Feel free to share this video. Please leave some helpful thoughts in the comments. And thanks a lot for watching.